Welcome to our channel. Today, we're diving into the fascinating world of calculus to learn how to find derivatives of various types of functions. Whether you're dealing with square roots, exponentials, or trigonometric functions, we've got you covered with clear, step-by-step explanations. By the end of this video, you'll be a master at differentiating them all. Let's get started. Let's find the derivative of the square root function using first principles. We start with our function f of x equals the square root of x. The derivative by definition is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. When we substitute our function, we get the limit as h approaches 0 of the square root of x plus h minus the square root of x, all divided by h. Let's visualize what this means graphically. Here's the graph of y equals square root of x. The derivative at any point represents the slope of the tangent line at that point. What we're doing with the difference quotient is finding the slope of a secant line. And as h approaches 0, this secant line becomes the tangent line. To evaluate this limit, we need to do some algebraic manipulation. First, we'll rationalize the numerator by multiplying both top and bottom by the conjugate of the numerator. This gives us the square root of x plus h plus the square root of x in the numerator. This simplifies to the limit as h approaches 0 of x plus h minus x over h times the quantity square root of x plus h plus square root of x. The numerator simplifies to h, which cancels with the h in the denominator. This gives us 1 over the quantity square root of x plus h plus square root of x. As h approaches 0, square root of x plus h approaches square root of x, giving us 1 over 2 times square root of x. Therefore, the derivative of square root of x equals 1 over 2 square root of x. We can verify this result by checking that this derivative gives us the correct slope at any point on our graph. For example, at x equals 1, our derivative formula gives us a slope of 1/2, which matches the slope of the tangent line we drew earlier. Let's find the derivative of 1 over square root of x using first principles. Our function is f of x equals 1 over square root of x, which we can also write as x to the negative 1/2 power. Let's recall the definition of derivative from first principles. The derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. First, let's find f of x plus h. When we replace x with x plus h in our original function, we get x plus h to the negative 1/2 power. Now, we can substitute these into our derivative formula. We get the limit as h approaches 0 of x plus h to the negative 1/2 minus x to the negative 1/2, all divided by h. To simplify this, we'll use the binomial theorem. First, let's rewrite x plus h to the negative 1/2 as x to the negative 1/2 times 1 plus h over x to the negative 1/2 power. Now, we can use the binomial expansion for 1 plus h over x to the negative 1/2 power. The expansion gives us 1 minus 1/2 h over x plus higher order terms. After distributing x to the negative 1/2 and subtracting x to the negative 1/2, we get negative x to the negative 3/2 over 2 plus higher order terms in h. Finally, as h approaches 0, all terms with h go to 0, leaving us with negative 1 over 2x to the 3/2 power. We can also write this as negative 1 over 2 times the cube of the square root of x. Let's visualize this derivative with a graph. The blue curve shows our original function 1 over square root of x, and the red curve shows its derivative. Notice how The derivative is always negative, which makes sense since our original function is always decreasing. Welcome! We'll find the derivative of e to the power of mx using first principles. This is a fundamental derivative that's important to understand. Let's start with our function. Let f of x equal e to the power of mx. Step 1 is to find f of x plus h. When we substitute x plus h into our function, we get f of x plus h equals e to the power of m times the quantity x plus h. Step 2, we'll use the definition of the derivative. The derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Let's substitute our expressions. Step 3. Let's simplify this expression. First, we can rewrite e to the power of m times x plus h as e to the power of mx times e to the power of mh. Then we can factor out e to the power of mx from the numerator. Step 4. Now comes the key insight. We'll use the series expansion for e to the power of mh. E to the power of mh equals 1 plus m h over 1 factorial plus m squared h squared over 2 factorial plus m cubed h cubed over 3 factorial, and so on. Step 5. Let's substitute this series into our limit. When we subtract 1 and divide by h, we get e to the power of mx times the limit as h approaches 0 of m plus m squared h over 2 factorial plus m cubed h squared over 3 factorial, and so on. Step 6. Finally, as h approaches 0, all terms with h go to 0. This leaves us with just m times e to the power of mx. Therefore, the derivative of e to the power of mx equals m times e to the power of mx. This is a powerful result that shows us that the exponential function is special. It's the only function that is proportional to its own derivative. When m equals 1, we get the even more special case where the function exactly equals its own derivative. Let's visualize this function and its derivative. The blue curve shows e to the power of mx, and the red curve shows its derivative, m times e to the power of mx. Notice how they're proportional to each other. Let's find the derivative of natural logarithm using first principles. We start with f of x equals natural log of x. Step 1. Let's define f of x plus h. When we replace x with x plus h, we get f of x plus h equals natural log of x plus h. Step 2. We'll use the definition of derivative. The derivative is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Substituting our expressions, we get the limit as h approaches 0 of natural log of x plus h minus natural log of x, all divided by h. Step 3. Now we'll use the properties of logarithms. The difference of logarithms equals the logarithm of their quotient. So this becomes the limit as h approaches 0 of 1 over h times the natural log of x plus h divided by x. Step 4. Let's simplify the fraction inside the logarithm. We can rewrite x plus h over x as 1 plus h over x. Step 5. Now comes the key step. We'll use the series expansion for natural log of 1 plus y. Natural log of 1 plus y equals y minus y squared over 2 plus y cubed over 3 minus, and so on. When we substitute y equals h over x, we get this expression. Step 6. Let's simplify by collecting terms with h. After rearranging, we get 1 over x minus h over 2x squared plus h squared over 3x cubed, and so on. Finally, as h approaches 0, all terms containing h will vanish. Therefore, the derivative of natural log of x equals 1 over x. Let's visualize this result. Here's the graph of y equals natural log of x, and at any point its derivative, or slope of the tangent line, is 1 over x at that point. Let's find the derivative of cosine 2x using first principles. We'll break this down step by step. Step 1. Let's start by defining our function f of x equals cosine 2x. Then, we can write f of x plus h equals cosine of 2 times x plus h. Step 2. We'll set up the difference quotient. The derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Step 3. Now comes the clever part. We'll use the cosine difference identity. The cosine of a minus the cosine of b equals negative 2 times sine of a plus b over 2 times sine of a minus b over 2. Let's apply this identity to our problem. We'll substitute a equals 2x plus 2h and b equals 2x. Now let's simplify what's inside each sine term. In the first sine, we get 4x plus 2h over 2, which simplifies to 2x plus h. In the second sine, we get negative h. For our final steps, we know that the limit as h approaches 0 of sine h over h equals 1. And when we substitute h equals 0 into sine of 2x plus h, we get sine of 2x. Let's visualize this result with a graph. Here's the original function, cosine 2x in blue, and here's its derivative, negative 2 sine 2x, in red. Notice how at the peaks of cosine 2x, the derivative is 0, and at the zeros of cosine 2x, the derivative reaches its maximum or minimum values. And there we have it. We've shown that the derivative of cosine 2x equals negative 2 sine 2x, both algebraically and graphically. Let's find the derivative of sine 2x using first principles. This means we'll use the fundamental definition of the derivative to find the result. Let's start by defining our function. Let f of x equal sine 2x. Then f of x plus h equals sine of 2 times the quantity x plus h. The derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now, let's substitute our function into the derivative definition. We get the limit as h approaches 0 of sine of 2 times the quantity x plus h minus sine 2x, all divided by h. To solve this, we'll use the trigonometric identity for the difference of sines. The identity states that sine a minus sine b equals 2 times cosine of a plus b over 2 times sine of a minus b over 2. Let's apply this identity to our expression. Let's simplify what's inside the cosine and sine. 2x plus h plus 2x equals 4x plus 2h divided by 2, which equals 2x plus h. And 2x plus h minus 2x equals 2h divided by 2, which equals h. Now we can split this into two parts. We have 2 times the limit as h approaches 0 of cosine of 2x plus h times the limit as h approaches 0 of sine h over h. Let's evaluate each limit. The limit of cosine of 2x plus h as h approaches 0 is just cosine of 2x, and the limit of sine h over h as h approaches 0 equals 1. This is a fundamental limit in calculus. Therefore, the derivative of sine 2x equals 2 times cosine 2x. This is our final answer. This result shows us that when we differentiate sine 2x, we get 2 cosine 2x. The factor of 2 comes from the chain rule, which we applied implicitly through our limit calculation. Thanks for watching. We hope you now feel more confident in tackling derivatives in calculus. If you found this video helpful, make sure to like, subscribe, and hit the bell icon for more educational content. Feel free to leave any questions or topics you'd like us to cover next in the comments below. Keep practicing, and see you in the next video.